The presentation is visible?
Yes, sir. Your presentation is visible. You can
Okay. Thank you, sir. So, myself, Dr. Deboraj Mucharry, currently with the NIT Raipur. Now, today I have chosen this topic, recent trends in solar energy materials and solar cells. As the theme of this event is related to the materials and devices, next generation materials and devices. So I have selected this topic, and I'll be covering only some partial parts of the whole theme, because this is a very wide area, and it's covering it's within the short duration of time is a issue. So first, I would like to mention the outlines of today's my presentation. So I'll be touching the introduction portion of the solar cell, then going to the brief history of the solar cells, how it has become a important part in our industry, how it has grown. That brief history I'll be discussing. Then the solar cell working principles, like what is the basic uh, uh, element of the working behind the solar cell, how it is working. So I'll touch a little bit of that also, and then I will move forward to the different approaches on silicon based solar cells. As we know that the silicon solar cell is a very leading technology nowadays. Whatever we are using in the our rooftop or in outside our the institutes or residential areas, so these all are consist of silicon based solar cell only, due to the reason of high efficiency. So, but there are some issues also. I'll be mentioning that, and how, what are the different issues, and how we can try to nullify that issues, or how can we remove that issues and we get an efficient device. That different approaches are there. So I'll be touching that also. A part of that will be touched by me. Then I'll be going to the modeling of solar cells. So basically the uh, fabrication process of this solar cell is very limited in India. So modeling is also a part, and is a tool for research, what we can do in our everyday this scenario. So modeling of solar cells, how it is done, that a part of that also covered in this outlines. Then the most trending topic, the most currently going on the research, it is a perovskite based solar cells. So nowadays people talk about the perovskite based solar cells, and it is a very promising candidate for the solar cells. And how these perovskite materials are constructed, how it is inside view of these materials, I'll be slightly touching, and then trending of these solar cells, perovskite types of solar cells, uh, it will be discussed, and then I have some references. So, going to the introduction part, as we all know that the solar cell is a very green technology, and it has a very limited carbon footprint. So it emits a very less, I mean, it's like a negligible kind of carbon footprint it emits compared to the other energy technologies, like our hydropower project, our wind power projects, thermal power projects, and any other renewable energy techniques. The solar cell is one of the uh, uh, top techniques we can call. So it is a environmental friendly. That is a very good uh, sign for us. Then in this, as we all know that this is the era of technology, and every day we are consuming lots of powers. Like we have mobile phones, we have laptops, we have tablets. So everything is consuming the power, and it's a high demand of the power nowadays, and people are going to uh, grab more and more power consuming electronic devices, as well as that this demand of power is also increasing. So one of the solution to overcome that power need is solar cell also, because it is a environmental friendly, as I have mentioned, and it is a renewable technology. So it's a kind of immense pillar to support the need of the power. Then technology has this technology has an advantage, beautiful advantage, and that advantage is that the flexibility to install. Like we can install this technology at every place in the world, every terrain, every place we can install it. Like if you have to install some power source at some mountain top, or some near your north pole or south pole, there also you can install that without any difficulty, because what you need to bring is you can install it individually. If it is off grid connected, like then you can install it everywhere, and that is flexibility is there. So that is one good advantage for us in the solar technology. Then one quote for from NRL, they said that solar energy received by earth in 1 hour is sufficient to meet the annual energy need worldwide. So whatever in 1 hour solar energy is received, that much power is sufficient to provide all the annual energy needs all about the globe. So this is a very powerful statement we have from the national renewable energy, this one. So I'll just have a glimpse of what are the different solar panel markets, how it is now, what is the scenario of the solar panel market. Just a few overviews there. So I have collected a PV market globally now. Uh, According to the EPA Solar Power, these are some agencies name of the resources where I found it. So these agencies do the survey of these different types of solar power consumption, and different types of not only solar but also the wind power and every renewable type of powers. They what is the current growing and what is the amount production, the things they take care of. So in the end of 2020, this last year, few years back only, so this globally now the value has increased to 138 gigawatt. Like this is the additional power in 1 year. So in 2020 only, 138.2 gigawatt power, PV based, photovoltaic based power plant has been established, so worldwide. So this is it is kind of a sign of growing the technology. Next, this 709.6 gigawatt, this much total power generation globally, as per the record of IRENA, this much power generation has been developed till that. Now, looking at this, our at a small scale in our national level, like in our India, we have seen that around 2110 megawatt additional power installation is done in the year of 2021 by June of this last year only. So this is the report from Indian Solar Compass. According to them, it is like 2110 megawatt of power. Then we have total power production in India is around 46,130 megawatt of the power. So these things are like growing every day and every year. So that this may change from time to time. So, but at the end of June, I collected this much. Now, next, PV electricity share. That means we have different sources are there. Like we have 10, 15 different sources of electricity generation is there. So according to the BP report, this 3.2% of the total energy generation is done by the PV electricity only. That is photovoltaic electricity only in the world. So it is the in the 2020. Likewise, I have found this power generation from PV in terawatt hours. It's around 855.7 terawatt hours. And lastly, we can see that the technology what we are dealing with is silicon technology, like crystalline silicon technology, and microcrystalline and polycrystalline silicons are also available nowadays. So altogether, this is altogether not only the crystalline silicon. So altogether, total 95% of the market share, the production of 95% solar cell is based on silicon technology nowadays, and that is from ICS market report. And this is a kind of like the old technology, and it is still going on in the market. But people are going to replace that and trying to replace that. That is the research in solar cell. So here I have some statistical data of the energy generations. Like I already mentioned in the earlier slide also that renewable energies is like around 3000 terawatt hours generations, and inside the renewable energy only we have solar cells. So this is worldwide on the left side, and we have power generations in the India only. It's also like some small scale, but it is growing. So these are the some pictures where we can see that how solar energy generations are growing. Now this I have kept for just remembering the discoverer of the PV effects. Like Edmund Becquerel was the first in 1839. He first discovered this PV effect in the electrolytic plates. Then several years later, like 1953, this inventor Kelvin Fuller, so he first used a pure silicon solar cell at the Bell Laboratory, and he created the solar cell using the silicon, and he got the efficiency of around 6% or 7%, some kind of that. So this is the journey plan journey of the PV cell to the industry. So it's like starting from Edmund Becquerel, it's going to the from 1839 onwards, it is going and developing like Wilbur Smith and founded photoconductivity in selenium. So the first material that people were using to build a solar cell was a selenium based, but now people have shifted to new technologies, new materials. So selenium has some lots of limitations, so people don't use it. And then a heterojunction solar cell means the solid state solar cells was first done by, I think, in the Walter Schottky in 1930. He first did that thing, and then slowly it is growing, and it is industrialization is done by 1955. So this is the story. Now let us see the brief working of a solar cell. So like this is a very simple diagram to understand how the solar cell is working. So it is a, as we know, the solar cell is nothing but a PN junction, the like a semiconductor PN junction, of a, which is made of silicon. So we know that the silicon can be doped in N type and P type, two different sites we have met, and it is a PN junction. So this is PN junction solar cell, so to say. Now we know the P side has a lots of holes, because the my majority carrier is the holes, right? And the N side has a electrons, and the minority majority carriers in the N side is electrons. So we have like this. Now when we make this type of junction between P type and N type, so there diffusion process takes place. So diffusion of the electrons from N side to P side will take place, as well as the diffusion of holes from the P side to the N side. It will again takes place. So it will be just like flowing of water from higher location to the lower location, like that, and it will be so that it will be neutralized, so that the concentration of the carriers will be neutralized. So I have just made some animations, like electrons diffuse like this side, and holes when it diffuses, it leaves behind some positively charged. This is fundamental physics only. So the positive charge will be leaving behind, and likewise the hole will be diffusing from the P side to the N side, and uh, eventually it will be developing some negative charge over there. So this is a kind of a electric field generated across this junction, and this junction has a positive terminal. Electric field is starting from the N side to the P side, and uh, this region is also called as a depletion region, or this is also called as a depletion region. So it is the normal PN junction under equilibrium conditions, right? Under not application of any electric field, not application of any voltage. This is the condition, we all know that. Now what happens is that when we expose this type of junction to the electricity, sorry, to the light. So when photons are allowed to fall on the junctions, when photons are allowed to fall on this device, then this device at inside this some electron holes will be generated. So electrons hole will be generated not only inside the depletion region, but it may be generated inside uh, these regions also, other regions also. But the major electron and hole generations inside the depletion region are the very important one. Because why? Because it is undergoing under the, it is remaining inside the electric field, and these electric fields are the main reason of drifting these electrons and holes apart. So whatever generated electron holes inside this depletion region, it will be drifted, like holes will be drifted towards the negative side, and electrons will be drifted towards the positive side. So they will move in two different directions in the p side and n side of the semiconductor piece. So this way, this electrons and holes, when it moves away from this junction, metal contact and the left side and metal contact at the right side, this will constitute one complete circuit, and it will generate one electricity. So this is the basic fundamental principle of the solar cell working. Now, let us see a deep insight of what is this junction is about. So we have depletion region, and here we know the electric field is there. Now, whenever we build a solar cell, it is not like that we can directly expose the light to the junction. The light will be either you have to expose from the left side, or you have to expose from the right side. So here I have assumed that the light is exposed to the left side of this device. Then how is the generation of electrons and holes takes place? So this light, when it is exposed to the x at x equals to 0, the generation profile will be this exponentially decaying. It is exponentially decaying, as it is shown by this generation profile graph. This is exponentially decreasing towards the end of the semiconductor piece. Now, what is the probability that these generated electron holes will be collected at these two end of the two contacts? So that probability is it is something like that. It looks like something like this. So it is high at the inside this depletion region. The maximum probability of carrier extraction, that is called carrier extraction also. So maximum probability of carrier extraction will be inside this depletion region. So those electrons and holes which are generated inside this depletion region, it will be splitted and it will be collected. And those who are generated which are generated far away from these junctions, they are also collected, but the probability of collection is less. It is decreasing on either side of this junction. So there is one limit of the distance, that is called diffusion length. So if the diffusion length of this semiconductor, it is around this much, then the every electrons and holes those are generated within this length, this will be collected, and this will be utilized as a solar cell electricity generation. And those who are which electrons holes are generated outside this range, they are very poorly collected, or they are most of the time they are not even get collected. So that is a limit decided by the material property. So this diffusion length is a very important property in our materials. So silicon has a good diffusion length, and some of the materials are having good diffusion length, like perovskite also has a good diffusion length, and the carrier diffusion length is good, so it is useful in solar cell. So that is one important parameter. Another parameter is the generation profile. So the generation profile, as much as the generation is high, the number of electrons and holes will be high, and so we have to we will get a good efficiency of the solar cell. So this is the previous side. Now the semiconductor equations. Now when we go for a modeling of a solar cell, like if we want to model some solar cell or some any kind of solar cell, we have to deal with some equations, and that equations all of you we know is that drift diffusion equation. So drift diffusion equation is constituted of one drift term and one diffusion term. So in every piece of semiconductor, when the carrier transportation comes into picture, then these two quantities are very important, like drip component and diffusion component. So the first term here is q and mu and e. This is the drip component, and qd del n del x is the diffusion component. So constitute current of n due to electrons and current due to holes. These two are met from these two terms in the drip diffusion equations. Next, we the very important equations we have to deal with is the Poisson equation. So the Poisson equation, what it does is it relates the potential with the uh, charge, potential with the charge, as well as we can say that it is relating the electric field with respect to the charge. So these equations I have written in 1D, one dimension. So it is in solar cell simulation we use 1D only. 1D is sufficient to find out the characteristics of different parameters. So 1D is a sufficient one, but if you want to go for more than 1D, like 2Ds is also good. So here the terms on the right side we can see is the P and N, ND plus, Na minus, and NDEF. So we all this P, N, ND, Na, these are coming from the doping profiles of the semiconductor. So whatever we are doping, accordingly we will get the number of electrons N and number of holes P. Now the question is that this term, that last term, NDEF is here, meaning is the this is the defect density. So defect density. So whenever there is a defect density, and most of the materials, like older materials, they have some defect density. No matter it is inside the bulk of the semiconductor or at the surface of the semiconductor. So this defect density, it plays a very important role while we go for the designing of the solar cell. So we will see that also in our future discussions. Now the next equation is the continuity equation. So the continuity equation, we know that here generation and recombinations are dealing with. So we have this generation term z and this u, and it is nothing but the recombination term. So after generation and recombination, with respect to time and with respect to distance, how these carrier concentrations are varying, that equation is the continuity equation, right? So let us move to the next slide. Okay, so before going to these overall discussions, we should see the current voltage equations of this device and the equivalent circuit. So a diode, a semiconductor diode equations we have seen is a constitute of exponential term. The current voltage equation is related to the exponential term. Now whenever we actually in practice we have some we designed a more device, then there is some series resistance will be there. So series resistance will be there, and as well as the sound resistance will be there. So the series resistance and sound resistance, these two have to be incorporated in this model. So we have a diode here, and the diode is it is a normal diode, and it is the current source due to light. So when light is exposed, the photocurrent will be generated. So this, there is one term that is IL, and this IL term will be taking care of this photogeneration current. And the rest part is, you see you have these diode equations and this series resistance and shunt resistance. So how does actually a current voltage characteristics looks like when they exposed to the light? So you have a current density J here, and you have a voltage over here. Okay, so the this J and V characteristics will be something like this. So it is due to the exposure of the light, it is shifting to some value. It is shifted with some DC value. Okay, so this value after shifting, it will be constituting like this type of graph, and this is in fourth quadrant. You can also draw the graph in the first quadrant also. So these things are defining the parameters of this device. Now what are the different terms we have to know? First is the short circuit. Okay, so the short circuit current, JSC. The short circuit current is nothing but this current where it is at the short circuit condition, where there is no voltage applied, where the voltage is zero. Then that means across this device there is no voltage. Then what is the current across this in the short circuit condition? That is the short circuit current. And one thing is there is that we all always define these things in the current density, right? So another parameter is the open circuit voltage, that is called VOC also. That open circuit voltage is the voltage when you have no, it is under open circuit conditions. Means when there is no connection of the external circuit, so it is openly kept open. So under that condition, the voltage across the device, that is the open circuit voltage. Now this rectangle, this rectangle is a very important parameter, because this rectangle is the maximum allowed rectangle which can be fitted inside this graph, inside this curve. And this area of this rectangle is defining as the maximum power that we can draw from the device, because the device has a voltage of VOC and current of JSC. So that if we convert into the power, it will be VOC into JSC. But that much power we cannot utilize. We can utilize only this much power which comes under this rectangle, right? So the voltage which corresponds to this uh, rectangle, that is BM, that is called maximum voltage, and current which is corresponding to this edge of the rectangle, that is JM, that is maximum current density. So these two parameters are the parameters which will define how much power we can draw from this device. So that is what is going on. Now, here, one more thing I would like to mention is that if we deal with the device, then we see that the current saturation current density, that is the recombination current, then dark current density, these things are also coming into picture. So whenever we design some device, then you should take care of these things also, because this saturation current density, if it is high, or if it is of the order of large value, then the device will be degraded, and you will find that the fill factor value of this device will be very less. So let us see how these are related. So here the four major parameters that we take care of is are the VOC, that is open circuit voltage. We have a short circuit current, right? JSC, denoted by JSC. Then we have fill factor, that is decided by the BMJM divided by VOC JSC. So what I have been mentioning is this only, because this is the power, actual power we can draw, and this is the total powers which is appearing. So these two ratios is nothing but this fill factor. So likewise, we can see in these VOC equations. So the VOC equations are given by this simple formula, that eta kt by q ln. So this JL is nothing but a light generated current, but this J naught is also coming into picture. So that is why I have been mentioning here that if you cannot reduce this value, if the value of the junction is of the value of, if the value at any junction is high, then the value of VOC will be definitely falling down, because you see this is inversely related. So whenever we have to deal with this type of design, then we should see the value of the saturation current density also. So next we have the parameter of JSC, that is short circuit current. So here this is the approximate equations, not the exact equations, but you can imagine how this is related with respect to the generation profile of this device. So you have seen this Z for generation. So the JSC is, of course, it is directly proportional to G. So as much as the generation is here, the short circuit current density will be high. As well as one more thing is coming into picture is this Ln and Lp. So these Ln and Lps are nothing but the diffusion length that I have been mentioning in that slide. So the diffusion lengths are also very important to boost up the value of the JSC. So in case of JSC, we need to take care of the generation as well as this diffusion length. But unfortunately, the generation and this diffusion lengths are material based, so we cannot do that anything, because everything its value depends is the material, is on material only. So we need to find the materials which are which have high diffusion length and high generation profile. And in case of VOC, you can adjust the VOC with the help of Zenot. So the defect density is the this saturation current density. You can put some techniques to reduce this value so that VOC will be boost up. And definitely the fill factor and fill factor is related to VOC and JSC. If you have increased these two values, then definitely these two values, the fill factor will be this one improved. Then we have the efficiency. The efficiency is nothing but you see the power converted to electricity, because we are in solar. What we are doing is we are converting the optical power to the electrical power. So when we are converting, means we have conversion of power from electricity to the optical power. So whatever incident power, the power that is incident to your device, that is optical power. So the total optical power is, suppose it is P, and whatever it is converted to electricity, that much power is your VOC into JSC into FF. So this much power to the ratio of P in, that ratio is called the efficiency. So you can have an idea how efficiently the conversion of power from optical to electrical is going on with the help of this parameter. So these all parameters are VOC, JSC, FF, and efficiency. So these all parameters are very, very important in the designing of the solar cell. So these are all about these fundamentals of the solar cell. Okay. So now we have seen the basic fundamental silicon based solar cell, but here you can find some problems, like your cost will be high, right? And it is a high temperature processing. So when you build up the silicon based solar cell, it is high temperature process, and it is the cost is also high, because the thickness of this material also there, and some other expenses is also there. So, and one more thing is that you cannot implement it in the flexible devices, like electronic devices, flexible devices. So these things are some problems nowadays with this silicon based solar cell. So people have been trying to replace this solar cell with the help of some other materials. So one approach is that we can reduce the thickness of the silicon if we make a heterojunction with other materials. So instead of doing a homojunction, and one more issue is that in homojunction, what you have to do is you have to do the doping also. So the doping of N site and doping of P site. So this doping process is also an hectic, right? So there is, if you have some other material and you make a heterojunction and the performance is good, then there is no need of doping of the homojunction. So that is why this another kind of approaches people have been doing is the using the amorphous silicon. So the amorphous silicon was the material that people used like 5-6 years back, but problem here is the one serious problem here is the Stabler-Wronski effect. Now Stabler-Wronski effect is that when there is exposure of light, when you expose the light for a long duration, then the device performance will be degraded, and that device performance, why it is degraded, because of this defect density inside this silicon, amorphous silicon, will be boosted up. So with the help of the light exposure only. So this is called light degradation. So this is named after Stabler-Wronski. So due to that problem, another investigation of another materials as a partner to the silicon has been going on. So this there are different approaches, like what we need is wide energy band gap. Why we need a wide energy band gap is that because when we expose the light to the solar cell, then the front layer should pass the light, and almost all the visible lights needs to be fall on the surface of the silicon that is lying underneath. So because the silicon has the absorption coefficient of wide absorption range, and it has a good absorption coefficient. So if we have a material of wide energy band gap that is kept on top of the silicon and the light is allowed to fall there, then the absorption of that light ray will be more effective. So that is why wide band gap energy materials are search for and optically transparent. So of course these materials like vanadium pentoxide, molybdenum oxide, tungsten trioxide, okay, ReO3, ZNO, thin SNO2. These are some materials. These are some oxides. Like these are transition metal oxides and this zinc oxide, tin oxide. So these materials are having a band gap of good wide band gaps, as well as they have a good transparency. They have a good transparency. Like in zinc oxide, you will find it's around 90% of transparency is there. So even more than that, it depends on the condition of the fabrication also, but the transparency is high, quite high. And the band gap of zinc oxide, you will find around 3.3 electron volt. So likewise, the band gaps of these materials are wide, as well as the transparencies are good. But there is that is why this has been investigated as a partner to the silicon. But the problem here is that it has the conductivity of these materials are less. Again, one more parameter that we need to know is the conductivity, because whenever the light is exposed to the device and electron holes are generated inside the depletion region or near the surface of the silicon, then these carriers need to be passed again through these materials, so that it will be collected at the electrode. And that depends on the conductivity, the electrical conductivity of the material also. So here in these materials, the electrical conductivities are, some of these materials are have average electrical conductivity, but some of these have less electrical conductivity. So like zinc oxide has a good transparency, but the conductivity is less. Tin oxide is a good conductivity, but it has the problem of like transparency is not up to the mark. Like it is not up to the whatever have zinc oxide have, up to that much it is not have. So these transition metals like B2O5, MO3WO3, these are used. Other polymers, another materials we deal with is the polymers. So the polymers like P3H3, P.PSS. So these polymers are also very highly transparent, and their conductivity is good also. So these materials are also used as a partner to the silicon, and that is why now when we use the these polymers with the help of silicon, that is called hybrid. That is why it is called hybrid. So it is a polymer and inorganic waste of solar cell. So it is a hybrid solar cell. So next we'll see like transition metal oxides. What is the current scenario up to the now, what people have done. So B2O5, MO3, and W, this has highly transparent to visible spectrum, as I have already mentioned. Then it has got high work function of around 5 electron volt. Now work function is also a parameter which is very important, because work function it helps in flowing the charge carriers. Like if the work function is matching, then the flowing of the charge carrier is good. Otherwise, if there will be a barrier, then it is a not good for the transmission. Right. So this transition metals has a high work function also, so it is good for transmission of the this carriers, surge carriers. Now another issue is the stability, high stability. These metals are highly stable. So whenever we fabricate some solar cell and we place it outside, if the stability is very low, it reacts with the environment. So it will be lasting for 1 year or 2 years. After that, it will be degraded, right? So the stability is also a very important issue in this designing of the device. Next is low temperature and solution processable. So as we know that these materials can be deposited with low temperature, and simple solution based techniques we can use. Other techniques like RF sputtering, DC magnetron sputtering, flash evaporation, sol gel techniques, PLD, spray pyrolysis. These several of technologies are there, deposition methods are there to deposit these metal oxides. And one more thing is that these are naturally n-type. So what is the advantage of this is that you don't have to doff it some materials. It by default it comes with some n-type materials, n-type of property. So like if you have to make a NP junction, so these transition metal oxides are n-type already, and if you doff p-type, you take a p-type silicon, then you can make a PN junction, heterojunction, and you can build a solar cell. So that is what one important parameters. Now, some other applications of these transition metals are like thermal sensing. Okay, thermal sensing is there. Then lithium battery, and then transparent conducting oxide. So what we are using here is called TCO also, and it is used in some other solar cells also, like organic solar cells, like in perovskite also. You will see that. So these are some introductory part of the transition metal oxides. Now, we can see a simple example of this work done by Carling et al. So this is a simple schematic of the solar cell that is based on this hybrid TMO silicon based solar cell. So TMO silicon solar cell, that is transition metal oxide silicon solar cell. So here this structure here you have seen is that the board at the middle, this main absorber layer, the light will be falling from the top because this is the front surface, and the middle layer here is the n-type silicon. So it is an uh, this is an n-type silicon, and this is made of this is crystalline silicon. Okay, so it has got some parameters like properties like this resistivity of 1.5 ohm centimeter, and its thickness is around 280 micrometer. So 280 micrometer thickness it is taken. Now, these are the steps they have used to fabricate it. So, first of all, they have done this texturization of this silicon. This silicon piece, they have done some RCA cleaning process and hydrofluoric diff. After that type of cleaning and texturization process, after this type of texturing they have done, they move to the PCVD technique, chemical vapor deposition technique. So, chemical vapor deposition technique they have used to deposit this rear contact. So the rear contacts are made of some these rear contacts are made using the PECVD method, and they have what they have done is they have made selective contact. A selective contact they have made. That is, they are laser using the laser fire to they have cut some small areas, and here only the contact is made. The contact is not made or at the whole place. It is some selected contact they have made. And why this used is that because this will help in reducing the surface recombination. So what is the advantage of this type of structure is that the contact is at this trans area. The trans areas here, the contacts are made, but at these positions, if you see these positions, this is not this directly metal contact. These are some passivation layers they are using. So the passivation layers are on the top of this silicon surface. So due to that, the surface recombination is a very low in this type of design. So due to surface recombination is less, the collection probability and all these things are good, and so the efficiency will be high. So this technique they have used. So here in this back surface, there is actually 3 layers are there. I think I have not shown it properly, but yes. So here is 3 layers they have used. The silicon carbide layers, that is, it is a passivating layer, the passivating layers, and then they have used a highly doped N plus region, highly doped region, and then third one is their bag reflector. So what is the bag reflector is that the light will be coming through this part, and then what happens is that the light when it reaches here, the light which are absorbed, the photons which are absorbed here, it is gone, but the photons which are not absorbed here, it will be striking at the bottom, right? So when it is striking the bottom, so the light needs to pass back. So it is like it is moving back. So due to that, one reflector layer is used here. So the reflector layer will reflect it, and the light will be accepted here. And this technique, after that, what they have done is that TMO thermal evaporation. So this transition metal oxides, they have thermally evaporated them. The thermal evaporation technique they have used to deposit these thin layers of like 15 nanometers layers of transition metal oxides. So transition metal oxides are deposited, and then on top of this they have used one indium thin oxide or ITO layer, and the ITO layer is it is a this conducting oxide, and this is very highly transparent but highly conductive also. And on top of this they have used this silver electrodes, 3 micrometer, and this back side they have used titanium aluminum, uh, this one metal contacts. So this is what the complete picture of a TMO silicon solar cell, and these are the process steps. And in this work, what they have done is like they have compared different types of transition metals. So using the same structure, using these same structures, they have used three different your this one. So efficiency table, there as per their work, it was like for vanadium pentoxide. This I'm calling it as a emitter layer, because in the earlier solar cells, this used to be a emitter layer. That is the top layer. We call it the thin layer. The thin layer we call it emitter layer, and this is the absorber layer in earlier solar cells. So that is why I called it as a emitter layer. So here, the emitter layers are these different materials, like they have used vanadium pentoxide, molybdenum oxide, and tungsten trioxide. So ReO3. These four materials actually compared, and it is found that these materials using V2O5, it's showing VOC of around 606 millivolt, 606 millivolt. Up to that much VOC they are getting. Then the current short circuit current density is also good. It's around 34.4 milliampere per centimeter square scale. Then what they have is this. Another one is the fill factor. The fill factor is around 75.3%. They have got the fill factor, and the efficiency is 15.7. So if we compare if you see in this table that these four different transition metals and corresponding efficiency, the least one is due to ReO3. The ReO3 has a least efficiency of around 2.1%, but the highest efficiency they have got is with V2O5. The V2O5 is the highest efficiency they got, and the reason is due to the high electrical conductivity of this layer. So V2O5 has the high electrical conductivity as compared to higher conductivity as compared to ReO3. And another reason is due to the interface recombination, the recombination at the interface. That means here is this tungsten transition metal oxide and this silicon. So at this interface, that is this junction, so this heterojunction, so some defects are there, definitely some defects are there. So due to that defect, this these different varieties of this efficiency is being found. So the best one they have mentioned is V2O5, and the worst one is ReO3. Now, what as compared to amorphous silicon? If this layer is not emitter layer is not transition metal, if it is amorphous silicon, that is also incorporated. Now, what is found here is that with amorphous silicon we got 18%, so it is quite high, right? So it is a 18%, it is 15%, so it is a quite high. So it means that you can see still there is a gap. Still there is a gap of what we are getting, because amorphous silicon, using that we are getting around 18.3%. So if we have to replace this problem, as there is a problem Stepler-Wronski effect. So if we have to replace these, uh, we will use these materials, but our efficiency is still low as compared to amorphous silicon. So there is a still gap is there. So if you're interested, you can do the work also, like doing some interface recombinations, minimization at this heterojunction. So by putting some new layer or some techniques, if you can provide there and reduce this interface recombinations, then maybe there's lagging behind the gap of this efficiency scale may be compensated, or it may be boosted high. So these things are the problems in this transition metals oxide based heterojunction solar cell. Now, I'm not discussing with others, other like zinc oxide and all this, because their efficiency is low, and their reason is that the this electrical conductivity. So there are lots of research papers also based on this, the developing the electrical property of electrical conductivity of these materials, like zinc oxide, tin oxide, like that. So recently, some I got some paper of nano composite, means the zinc oxide and SNO2 composite, and they used with the help of solar cell, with the help of silicon. So this type of works are there, but these efficiencies are quite low. It's below 10%, even it's like 5-6% like that. So this is that is why I have not discussed here. Now another good one is the P.PSS. So this is a polymer. This constitutes of two different compounds like P dot and PSS. Okay? So what is the advantage of this polymer is that it is a commercial this TCO also, transparent conducting oxide also. So here we have seen that P dot PSS, it is highly optically transparent. So it has highly optically transparent. So what is transparency is around 90%. 90% of transparency. T means transparency, or at 550 nanometer. So at a wavelength of 550 nanometer, the transparency is around 90%. And what in our solar spectrum, if you see in our solar spectrum, that the highest peak, the peak of energy of the AM 1.5 1.5 solar spectrum, that is where you see around 600 to 500, between 600 to 500, there is a peak intensity, right? So at around peak intensity of the solar spectrum, that is at around 550 nanometer, that is 550 nanometer wavelength, the transparency is around 90%. So it is a good transparent. So if you use it at the top of the silicon, then the light can easily pass through it, and it is falling on the silicon that is underlying. Next is the advantage. Another advantage is your in this P.PSS, that is your uh, mechanical flexibility. So the mechanical flexibility, why it is required? The mechanical flexibility is because you see the nowadays electronics gadgets are coming, which are flexible, right? And you need the energy source of energy resource in some flexible devices. So these semiconductor, this is sorry, these polymers are very flexible. These are good to be used as a flexible device also. So that is why it has a popularity. So that is one good property, that is a good mechanical flexibility. Next is the smooth surface. Now what is the smooth surface is that you see if there is a rough surface, then the recombination is high, the surface recombination is high, and if the smooth surface is smoother, then the recombination is less. Because the surface, when you are dealing with a semiconductor surface, at the surface the molecules, the atoms, the molecules will be what they will it will be terminated. The crystal structure of this material, sorry, the crystal structure of these materials will be terminated at the surface. So when you go through the materials and you reach the surface, there will be several dangling bonds are there. There will be several incomplete bonds will be there. So these things are creating the recombination centers for electrons and holes. That is called surface recombination. Now if you have a rough surface, that means your termination of this crystal structure is roughly, that means your recombinations will be high, and as the surface recombination is high, then the device performance will be degraded again. So it is highly related. So this P.PSS, this has a smooth surface also. So again, it depends on the no doubt it depends on the fabrication conditions, different growing conditions and all this. But on an average we can say that the surface of P.PSS is a smooth, and that smooth surface helps us to design in solar cell. So there is one another advantage of the P.PSS. Next is like high work function. So high work function, the work function is around 5 to 5.2 electron volt. So this 5 to 5.2 electron volt, these are suitable for the whole transport layer. Means they are used in even in some organic solar cells, and in perovskite solar cells also we see that these materials are useful as a whole transport layer because of this high work function, like in the value of 5. 5 is the the work function of gold. The work function of gold is 5, and it is used as a electrode in some perovskite solar cells also. So it is approximately near to that gold also. It is even more than gold also. So this work function of whole transport, this helps as a helps us to use this material as a whole transport layer, as a whole transport layer. So that is one good idea. Next is wide in electrical conductivity. Now, as I have been mentioning, that electrical conductivity should be good, Now this P dot PSS, it has got a electrical conductivity in the range of around 10 to the power minus 2 to 10 to the power 3. So this range is not fixed, this is tentative. Means on an average, you can say that it's within this range or nearby this range. So it has a wide electrical conductivity range. So you can see it, it's even 10 to the power minus 2. It's a small value, right? And it can go up to 10 to the power 3, that is 1000 times in Siemens per centimeter. This conductivity value can be. So if you have this much of conductivity and the transparency is also good, so definitely it will be a good tissue, transparent conductivity. So that is a good feature or advantage of the P dot PSS. Next is your like I have been mentioning that this homolumo layers, that higher orbital molecular, then lumo. So these things are this mass and 4 feet of PSS. Next, you have seen this. One more thing is that low temperature deposition, because these are polymers, and we when we go for silicon processing, the silicon processing is around 1000 degrees centigrade or more than, even more than that. So these are very high temperature processings, and there, what happens is that due to doping process only, this type of high temperature process is there, and what happens is that some of the problems arises. And here, if we use the P dot PSS as a deposit as a partner, then you can deposit it in low temperature environment also. So there is a good advantage in terms of fabrication point of view. Next is your good photo and electrical stability. So like you have like in amorphous silicon, we have photo stability is less. Photo stability in the sense it has light degradation effect. So when light is exposed for a long time, it will be degraded. So that is a problem. But this type of problem is not here in PDOT cases. So it is a good photo stability, as well as it has good electrical stability also. So the stability of PDOT PSS is not very bad. It is good, so to say, but it is not the best also. I will not say it is the best also, because it is a polymer, so definitely some problem will be there. But a good and it's average, like middle of this stability terms. Next, what we have is the sheet resistance. The sheet resistance is also, we know that as the conductivity is high, means the sheet resistance should be low, because these two are interconnected, right? So the sheet resistance is typical value is around 25 ohm per square. So this comes around 25, hence it is a low sheet resistance. So all these properties, all these parameters or properties, we can have a glance of how effective the feed of PSS is. So here is the it has got lots of applications, but we can use it in the solar cell development also, solar cell also, right? So excuse me. Okay, so we have here the chemical structure of feed of PSS. So it is made of two different uh, compounds. Here you see this below one is the polystyrene sulfonate, that is what we call PSS, polystyrene sulfonate, and the upper one is P dot, that is full form is poly 3,4 ethylene dioxythiophene. Poly 3,4 ethylene dioxythiophene. So this P dot and PSS, these are interconnected with this type of structure. So this PSS is a PSS is like it helps in it helps in your this dispersion of this P dot. So P dot is normally it is not solvent. It is not soluble in most of the solvents like water. In water and in some other solvents, it is not easily soluble. So this term, this polystyrene sulfonate, the PSS, it helps in dispersion of this P dot, and it helps in stability also. The stability of PSS is also improved due to the PSS chain here. So this PSS chain is something like it is blocking the stability. It is improving the stability of P dot, as well as it helps in dispersion of this polymer P dot in the solvent. So, so that it can be soluble in water, it can be soluble in alcohol, it can be soluble in some solutions. So when it is soluble, then we can use it as a using spin coater or some kind of techniques. We can deposit it. Like so, this is the fundamental structure. And one more thing is that PSS acts as see here is the negative ions, and this P dot has a positive ion. So this ionic process is also there. And one more thing is that this was, deposition of these techniques are like that is why it is at low temperature deposition is also possible. So this is I'll not go in deeper of this chemical structures, but this is the how the chemical structure of a PDOT-PSS looks like. And now here I have some data that is I have got from your. Here I have got some data, and this is the roadmap of PDOT-PSS. That is how it has been this type of solar cell, that is PDOT-PSS and silicon. This heterojunction, how this heterojunction solar cell, it has been growing, or it has been following the path in the year wise. So I collected some data from like I have collected some best efficiency, good efficiency one only. There are several, like in 2013 lots of papers are there, but the efficiency which is good, or I found the highest one that I have kept here. So as we can see, 2013 onwards up to the 2020, this efficiency of this type of PDOT-PSS and silicon type of solar cell, it is around 13%, or it is more than 12%. You can see here as in 7 they have declared it up to 13% efficiency they got it, and in 8 they have shown that around 15.2% of the efficiency is they have got using this heterojunction, that is hybrid solar cell. Next, in 2015, they have shown 14.14% percent of the efficiency in this technology. And the next one in 2016, the 10, they have showed that it's around 14.7% efficiency. Then in 2017 is 2017, I got the maximum value of around more than 17. It's something like 17.2 or 3, something like that, but it's around 70, means it's quite near to amorphous silicon based solar cells. Like we have seen in here, 18% amorphous silicon solar cell was giving, so 18-19% are available there. So it's like quite improved. But again, this 2018 some paper in 2012, they have represented it around 12.19%, and then we have in 2019 we have this 15 percent in 13, and then 14. So obviously these are not like same platforms, like they are not using the same fabrication technology, they are not using the same this the platform. So there is different platforms, but I am concentrating on these PDOT-PSS and silicon heterojunction, the solar cell which are based on this hybrid junction, that only I have collected. And there definitely the technologies will be different. So that is why this after 17% they have got 12.19%. So there is some technology differences there. Fabrication technologies and deposition technologies are different. So of course the values will be vary. But what is the what we can have a understanding from this picture, The basic understanding we can have from this picture is that on an average you can see this hybrid solar cell has an efficiency of around 15% or 14% kind of things. But yes, if you have some sophisticated technology, sophisticated techniques, then of course you may have grown it more than 17% also. So that you can close up to 20% or 19% like that. So still some works is need to be done because the gap is low, because now you can see uh, the limit efficiency limit is around 30%, 29%. So if you have to go to 29%, it's way beyond, right? So there is some still need of some uh, improvement. Lots of improvement is need to be done over here. So that is the issues. Now this is simple example how people have tried to rectify that. Like there is actually when you are working with these hybrid solar cells, then you see that silicon is here at the middle, and then p.ps on the top, and then silver grid, this contact silver grids are over here, and then at the back we have aluminum contact like this. So this is the schematic of the device. Now what they have done is that instead of direct making a contact with aluminum to silicon, they have used this one chemical, there's lic liq, and its full form is 8 hydroxy quinolinoleto lithium. So this is the chemical structure of this compound, that is lic compound. So this type of this type of material they have used this in between these aluminum and silicon contact. And the what is the advantage of using this is again the reduction in the defect density. So the defect density at this interface, or this back junction, back contact, that is actually a back contact. So at this back contact, the recombination surface recombination on the silicon surface is high, and that is why the again the efficiency will be falling down. So that is why they have used this leak layer, and this is the schematic of energy band diagram. So what is going on here is that, like p dot pss and n type of silicon they have used as a um, your Schottky type of contact. So p dot pss is a highly conductive, right? So it has good conductivity, so it is acting they have assumed it as a metal. They have used as a simple metal contact. So it is like a Schottky contact. So what happens is that whenever light is falling, the electron hole pairs will be generated. Now generally the electrons which are generated, okay, it moves in this direction, this photocurrent, this green color. So electrons move towards the n side and hole moves towards the p side. We have known that. So this is the normal condition, this green color lines. But what happens is that due to this energy barrier is low, or there is some uh, Schottky barrier, if the barrier height is low, then what happens, some of the electrons generated, it can cross this barrier, it can overcome this barrier, it can overcome this built-in potential over here, and it will go there. And likewise there is some leakage current, that is if there is some recombination over here between the aluminum and silicon, if the recombination centers are there at the surface, then these holes will be recombining with the electrons, and so it is a leakage current. So this dash line, dash lines are leakage current. So this is undesirable currents. So that is what at the rear surface, if you see this aluminum and this n-type silicons, it has got like smooth part, because the holes can easily pass through, and it can recombine with electrons, and a current will be flowing like this. But due to use of liq layer here at the rear side, the LIQ layer here, it is building some small potential over here. So the potential is increased somewhat, and due to that, the hole which are going to recombine here, it is undergoing some hindrance. It is undergoing some restrictions. So due to these restrictions, hole cannot pass it, or some holes will pass it, but some holes will not pass it, and it will remain here, and we will reduce the recombination loss. So that technique they have implemented using this type of structures. Okay, so speaking of this performance of this type of device, I'll not the device performance or the efficiency is like around 9.4, 11%, 12%, and 11%. So with the help of this thickness of this layer, they have what they have done is lick layer thickness. They have buried 1 nanometer, 2 nanometer, 2.5 nanometer, and say show the different parameters. And these are the junction parameters, because this is a what this is a Schottky barrier, Schottky junction. So of course there will be Schottky barrier, there will be saturation current, there is ideality factor. So these are the values they have found. So the thing to be noticed is that the recombination current is of the order of 10 to the power minus 9. So 10 to the power minus 9 is a good value, so to say. Now this I will not touch it, because this is just the discussions how the thermionic emission process and is going on at this interface, and what is the different parameters we need to consider. As I'll skip it. Now here I have collected some papers from 2013 to 2021, and I have seen here that lots of materials like at the rear interface, some materials like this are used at the intermediate materials and the front materials. So what is this meaning is that, so if uh, you have inserted something here in between this terminal, this heterojunction, if you have inserted something, that means what, there will be some this front, that is called front interlayer. I'm saying it front interlayer. If you are inserting something here, there is rear interlayer. And if you are inserting in between this silicon and p dot pss, then it is intermediate layer. If you are inserting between silver and p dot pss, this is front interlayer. So like this, like that, if we see it, then we have different, like rear interlayer, these materials they have used, and front interlayer, these materials they have used, and intermediate material they have used these type of things in these various papers. So efficiencies are trying to be improved. Now the modeling of p dot pss. So the modeling of p dot pss is like I have this taken this from yeah, this simple model. Like you can take p dot pss, n type silicon, indium gallium, and what here is the, you can use a back surface field layer and plus layer, so that the recombination at this back interface will be less, and one MOO3 layer if you are using, that is anti-reflection. Anti-reflection means the reflection here will be less. So this type of techniques they have used. Now how to model it, just you can do the modeling in two sections: optical modeling, electrical modeling. So the optical modeling here, again whether you can use Maxwell's equation, solve the Maxwell's equation using some techniques like FDTD, and then find out what is the absorption, reflection, transmission, generation, these things inside this device, and you can find out these parameters. Next is your electrical modeling, so I'll be discussing that. And nowadays simulators are there, right? So simulators are there, so you can insert the nk values of different materials. Like these are the nk values of p dot pss, this is the nk values of BO3. So if you want to simulate that structure, you need to put these values in the simulators, like these nk values, and the calculations will be done. Now here I have some data of reflectance, like this collected from this paper. This our red one is the experimental, and this is the simulated. So what they have done is that they've used FDTD methods and find out the reflectance from that device. And with the help of, if you get the reflectance, and if you as transmission is like 0, then you can easily calculate what is absorbance, right? And from this absorbance you can calculate what is the EQE, that is external quantum efficiency. So this type of graph for external quantum efficiency is observed. Now when you have different layers, like in this structure, let me go back. So in this structure you have different layers. So absorption here is different, absorption here is different, so recombination loss here is different. So if you want to individually check the different layers, different absorptions here, so you can use this type of equation, like q pi is nothing but a photon flux, and q is the like EQE. You have EQE or reflection profile or absorption profile, then you utilize that values here and you integrate within the range of the wavelength, you will find the corresponding current. So these things are you can analyze. Now we have a generation profile. Now I have been mentioning that the generation is a very important parameter. Like generation you can calculate in two ways. One, using FDTD you can find out this using this equation. Here you see E is the electric field. So you will be needing the electric field. If you have electric field, you can calculate the value of Z using this type of formula. Otherwise, if you have absorption coefficient alpha, using this formula you can calculate the generation also. And alpha is given by this type of modeling, that is square root model, and AB are some constant parameters that you have to define from the practical value. Now we have the recombinations. I think recombinations are, what are the different recombinations, like SRS, Sochleri Hall, band to band Ozer. These recombination models you can incorporate in the simulator or in your program. Then this is done, work done by us in recently 2021. So what we have done is here, the here we have checked the like same structure we have done in the simulator. We have used this back side. We are using this SNO2 layer at this back side between silver and this side. And this practically done in a paper 18. It was already this type of structure was already done. So what we have done is we have matched simulation curve with the practical curve. So these are practical curves, and overlapping is the simulation curve. So we have done approximate matching of the simulation with the practical, and we calibrated the device. So the device calibration is done. After that, what we have done is we have studied the effect of this interface defect density, effect of temperature on these IV characteristics. So these things we have done. So these are the parameters we have inserted into the simulator, like electron affinity, permittivity, band gap, density of state, hole mobility, electron mobility. So these things you need to put inside the simulator. And finally, we have done this type of analysis, like effect of interface defect. So with the increase of the defect density, how this JSC is changing, and how VOC is changing. And likewise, we have seen also the efficiency, how efficiency is changing, and how fill factor is changing. So here we have found that all the parameters are falling down, but except the fill factor. The fill factor is increasing, and the fill factor is increasing, and that is because of the, we have found out that this is due to the reason of your this work function problem. So this is one observations we have seen. Then here what we have it the same structure, what we have done is we have varied the electron affinity of that layer, electron affinity of this SNO2 layer. So SNO2 layer, we have varied the electron affinity, and we have seen the efficiency. And if the electron affinity is within the 3.8 to 4 around 4.6, within this range the value is high, like around nearly 14%. But below that and above that, the value is falling down, the efficiency is falling down. And the reason here is like that, if you have this ETIL means SNO2 layer. So if you have SNO2 layer here, and SNO2 layer has a this work function of which is above this Fermi level, then definitely electrons will come here. And then what happens, there is potential is generated here, a small potential will be generated here. And here is of course junction potential is there. Now this junction potential and these potentials are in like a series connection, so the overall potential will be improved. So due to this overall potential improvement, the this efficiency is remaining here, there's at high value. But what happens when this is below that, then the opposite process happens. That is what this electrons will be jumping from here to here, and this polarity will be changing. This polarity will be changing in the sense that this side positive, this side negative. So what will happen is that the overall potential between these two will be reduced. And that is why after when we increase the this electron affinity, it is falling down like that. So these things we have observed in that paper. Now in these scopes in the PDO PSS, these are like light harvesting through nanostructures. Like at the top you can do some nanostructures that people have already done also. Some nanostructures at the top, and junction area recombination can be reduced. Then increase the electrical conductivity of PSS by means of doping this or changing the chemical structure. If you can increase the electrical conductivity of this further, then definitely the conductivity, the efficiency will be high. And tailoring the interface, like whatever we have discussed, that is the tailoring of interface only. So we have changed interface quality and seen the then say this one, fill factor, efficiency, depth parameters. So this is all about I have to tell you about this hybrid solar cell. Now I won't take another 10 minutes I will take, I think, so to show the just briefly in this perovskite, another type of solar cells, the perovskite solar cell, how it is going on, what is the current research you can do. So here I will not go through too much because it's quite known to everyone. Like what is perovskite? So perovskite, I think one session has already there with Dr. Laxman Raju sir. So he already have delivered some lectures on perovskite, I think. So I'll not go in deep on that. But how we can utilize it, or how what are different areas you can do uh, research in the solar cell, that I will mention here briefly. The introduction to perovskite, yeah, like this is the chemical structures we know. ABX3 is some like methyl ammonium, formamidinium, like that. Then B is some like lead and some other materials also. It's there, like you have some tin or some others. And X is like you have halides, halogens, chlorine, bromine, iodine, like that. And their band gap are tunable, so you can tune the band gap. It's approximately for this it is 1.55, but you can tune it with the help of chemical structure here. Then absorption coefficient is quite high because you see it's around 10 to the power 4 to 10 to the power 5, so it's a good absorber of the light. Now it has three phase. According to the temperature, you see the below 160 you will get orthorhombic phase. Within this range you will get tetragonal phase, and above 327 is around cubic phase. So these all three phases has different optical and electrical properties also. So this is also again a huge area of study. Then a low temperature solution processable, and preparation method, one step, two step coating methods you can use. Now these are the different types of perovskites. I'll not touch that. This is the cubic phase perovskite structure. In the cubic phase, how it looks like. There is a uniform because it is a cubic phase. In orthorhombic, you will find this is somewhat the structure will be bending left or right, like that. So different phases a different structure, but this is just like a cubic phase perovskites. Now, trends in perovskite solar cells, what I have found as a trend in solar cell is that, first of all, interface engineering. So, what is interface engineering is that we know that perovskite solar cell, it has one side, it is electron transport layer, another is hole transport layer. So, here what we have seen is that between this C60 and C60 one layer, transport layer, and this is the perovskite layer. So what is in this recent work, in recent work they have in 25 they have given this layer, AAL layer. This AAL layer, some chemical compound they have used, and what they have done is conceptually I'm showing it that this electrons, these are tunneling through this AL layer is some dielectric layers. It cannot conduct the electricity, but the thin layer of this is placed here, and what happens is that due to this thin layer, this tunneling through this is possible. At the same time, it passivates the surface of the perovskite, because this surface of this perovskite, again here is some defect is there. So if some defect is there, the recombination will be there. So this AL layer will be passivating the surface of the perovskite here, as well as it allows the tunneling of the electrons towards the LUMO of this C60. So it is electron transport layer, ETL, because electrons are transported to this layer. So this C60, it is going to the LUMO of the lower unoccupied molecular orbital of the C60. So that is one thing. Now here what is the problem is that, here the problem is that it is in 2020 paper only, I think, and this is also the 2021 paper. So what I have found here is that they have used this tunneling. Here it is tunneling, but the thing is that at the same time the series resistance of this device will be increasing, as you see, because it is an insulating layer. So if there is some insulating layer, then the series resistance will be definitely increasing of the whole device. So that is why this new technique they have used, what they have used is, instead of doing this complete this blocking of this layer, means placing the whole layer uniformly here, what they have done is they have done some like uh, like C60 TiO2 is also electron transport layer. So what they have done is that yes, some nanostructures they have done like this. And what is the advantage of this structure is that it is like some layer is there, this perovskite. This is the perovskite layer, top layer, and this is the TiO2. So instead of completely putting a blocking layer here, they have made a hole in between these. So a small hole where they have inserted the TiO2 nanostructure. So TiO2 nanostructures will be inserted here, and it will be inserted inside the, it will be connected to the perovskite. So this way, the reduction of the series resistance is good, right? So the series resistance of this region will be reduced. So that way, they can improve these things. So there is one approach, the interface engineering. So this is just an example of an interface engineering. Next is transport layer engineering. So in transport layer engineering, what they have, what we can do is that in transport layer engineering, this yes. So now people what use is like spirometer. Before going to this, I should show you some of these. Yeah. So like 5 point. These are some transport layers. These are some transport layers. So these transport layers are used to transport the carriers. Now here what happened, this is also spirometer is also a transport layer. So this is a perovskite from a medium lead iodide. So it's a homo lumo values are there. Now spirometer, if you use spirometer, the Venn diagram alignment is something like that. So what happens is that this gapping, this is the whole will be transport from here to here, whole will be jumping from here to here, but this gap is somewhat large. So here is some loss in the open circuit voltage. So what some people have done, these papers, so they have done, they have modified this chemical structure of this pyrometer. They modified the structure and they have developed these two corollary. And what is the thing is that they are these labels, homo lumo labels are pushed down, and that is exactly like near to these homo and lumo levels of this perovskite. So it is better transport of the electrons and holes are taking place. The transporting of the holes from here to here will be taking place in a better way. So that is why they have found the efficiency of around 23.44%. If you using the normal spirometer, they are getting it 23.44. If they are using Spiro MF, it is getting 24.82. It's 24.5. So it's a bit improved from 23 to 24 is a improve, right? So this is another area. Now is a lead-free perovskite. So another area is lead-free perovskite. So whatever higher efficiency, the confirmed efficiency is now around 25.5 or something. So 25, more than 25 nowadays. So that perovskite are lead based. There's lead is used here. So the lead is used here. Now what is the concern is that lead is a toxic element. So lead free perovskite is a demand on demand now. So what are the different materials to replace lead? These are tin, antimony, bismuth, titanium, germanium, copper. These materials are being used instead of lead. But the problem is that their efficiency is less. Okay? Their efficiency is less. So there is a glimpse of different materials. That is your these are the perovskites. This thin based perovskites, MASNI3, MASNI2BR1. So this thin based instead of lead, here it is thin based. So this 1, 2, 3, 4, 5. These are thin based perovskites, and these are some hole transport layers, and these are electron transport layers. So these different materials combinations, the combination of different materials can be used to construct this type of lead-free perovskite thin-based solar cells. So that is one thing of. Now some of the efficiencies which are thin-based, I've considered only double-digit efficiency. That is thin-based perovskites. It's showing around 12% of the efficiency. So it is quite low as compared to your 25% in the lead-based perovskite. So another concept is the tandem-based solar cell, tandem all perovskite. So tandem means what? It is the combination of two different, two cells are there, one at the top, one at the bottom. So these two cells are there, and they have what they have done. What is the concept behind is that here the recombination of holes, like This side you have one MAPB BR3. This is one perovskite solar cell. This is another perovskite solar cell. This is bromine. This is lead bromide. This is lead iodide. So two different perovskites are there. So what happens is that when light falls on here, the light will be passing through this and it will be reaching here also. So carriers will be generated here as well as here also. Now what happens is that suppose the electrons is generated. Now what happens? Electrons will be the electrons generated in BR3 will be jumping from here to here, and holes will be jumping from here to here. Similarly, in this solar cell, the electrons generated here will be jumping from here to here, and holes will be jumping from here to here. Now the question is, what happens to this hole and this electron? So the thing is that when this hole and these electrons recombine, then the current will be matching, and the whole currents you will get. So hole and electron, when they recombine, that the current will be complete. A complete current will be obtained. So that thing to obtain this proper recombination of electron hole, one solution is that P3 has this layer should be thin. This should be thin so that this hole and these electrons will recombine easily. That is one solution. Okay, but the this making thin is also not a solution. Means there is some problem also. So one thing is that you need to put some you need to increase the mobility of this layer also, so that holes which are jumping from here to here can easily move and it will recombine with the electron coming from here. So the
Okay, I think speaker has some network issues. We will wait, otherwise we will ask, ask, ask for the wind up. Please stay online for 2 minutes.